Hello everyone, today I'd like to continue the discussion on how to write the correct Lewis structure. In this case, resonance structures in the formal charges. We'll address the resonance structure in the previous vodcast, and as we can see, some of the Lewis structures, we can have multiple possibility of distributing the valence electrons for the whole molecule or the polyatomic ion. And as we learned it before, see, like the Lewis structure for water, you will have go through the steps, first counting the total number of valence electrons, then you decide which one should be the central atom, then you link the surrounding atom with the central atom and count how many valence electrons you used for that purpose. Then you're looking at have you have any of those valence electrons left. Then you start filling towards the octet rule from the outside in, which means you satisfy the octet requirement for the surrounding atoms first, and then if you have any of the valence electrons left, dump them on the central atom. If you do not, then you got looking at the central atom. Now you're going to, for the next step, you're going to check on the central atom to see the central atom achieve the octet. And if they not, then you'll start forming the double or triple bond if the carbon, nitrogen, oxygen, phosphorus, and sulfur, and rarely chlorine are involved. So those are the ones, the process. If it's a polyatomic ion, the last step will be bracket and put a charge on it. So for instance, like water, you'll have a Lewis dot structure of the central atom will be the oxygen, two pairs of unshared electrons and linked with hydrogen, And then let's take a look at a carbonate. There was a 2 minus. You go through all the steps. Now you see the proper Lewis structure will be like this, and this has a 2 minus charge on it, and also you'll have the resonance structures. 3, 4, 5, 6. Now you have the double bonds here. Now you have and 2 minus, and this is going to have a Lewis dot structure. 3, 4, 5, 6. O double bond on this oxygen, and 2, 3, 4, 5, 6, and this has a 2 minus. As you can see, those are called the resonance structure, and this gives you the different possibilities of distributing the valence electrons. However, you know this has the 2 minus charge, but we actually don't know where the charge is coming from among those 4 atoms. Is it on the carbon, or is it on the oxygen, or which oxygen atom is this kind of the 2 minus charge are coming from? So this kind of question remain unanswered. And now let's take a look at sulfur dioxide. You go through all these steps, counting all of them up, and you will have a Lewis dot structure, a double bond here, and this is for the SO2. That's one of the resonance structure. Everybody's happy. Everybody's have an octet, 8 electrons surrounding sulfur, 8 electrons surrounding oxygen, 8 electrons surrounding the other oxygen. You should be happy, but as you know, the sulfur is on the 3rd period, and the 3rd period have the 3d orbitals available for bonding, and it actually can take more than 8 valence electrons. So that's the reason why for third period and below elements, they can go to expanded octet. If I actually go to expanded octet, you can actually have this particular resonance structure by forming a double bond here with a pair, forming another double bond here with the oxygen. But then coming down the question, which one of these two valence the Lewis structure is the preferred one? So you kind of have two questions. The first question is for polyatomic ions, which actually those atoms carries the charge, and for some Lewis structures, which of those Lewis structures should be the, what we call it, dominant one, should be the one that is preferred. So this is the one actually require you to understand a concept about formal charges. This is the way of keeping track of the charge of each surrounding of each atoms in the molecules in the polyatomic ions, but this has to be separated from to the net charge on any polyatomic ion. It's the charge assigned to each atom in a Lewis structure. So here is the the outline of the process, how to assign formal charge for each atom. So first you write the Lewis structure for the molecule polyatomic ion, and remember they potentially have multiple possible resonance structures. And now then you actually start counting the valence electrons on each atom. So it's two steps process. You already have some of the valence electrons surrounding the atom, put them aside, and they are linked. The surrounding atoms are linked with the central atom. Then you split the bond. If it's a single bond, you split 1 and 1, because each bond carries carries about 2 valence electrons. So you split them and then just give one to the one atom, give the other one to the other atom. If you have a double bond, split the 4. It's 2 for each. Triple bond, 3 for each. Then you add all this to the existing valence electrons on the particular atom. So now I have a total number of valence electrons on the particular atom. And you know from your previous knowledge about the atomic structure, electron configuration, now you can have Lewis dot structure for those atoms. And now you know for the neutral atom how many valence electron it should have. And then you compare these two numbers. If the number of valence electrons in the molecule in the polyatomic ion for this particular atom is more than the neutral form, you have a negative charge. If you have the number is less than the neutral form, you have a positive charge. So it's kind of a fairly easy to gauge. So let's give you an example just to showcase that. So let's take a look at water. Water, you now have this Lewis dot structure. Okay, so for each hydrogen, you change the color to follow on the Lewis dot structure. So for each of this, you assign a valence electron here, another valence electron for the oxygen, a valence electron for hydrogen, another valence electrons for the oxygen. So for the hydrogen on those, each will have 1 dot. For oxygen on those, each will have 6 dots. Okay, so for the oxygen on this, each will have 6. For hydrogen, each have 1. But remember, for a neutral atom, the Lewis dot structure for hydrogen, you have 1 dot. For oxygen, you'll have 6. So in this case, formal charge on the oxygen will be hydrogen will be 0 because it has 1 dot. It has 1 dot. It's no difference. So 0 on the oxygen, you will also be 0. You will also be 0. So let's take a look at the change the color back. Erase this. Let's change the color back. Let's take a look at carbonate. Remember carbonate? We have one Lewis structure like this. and 4, 5, 6. Oxygen 1, 2, 3, 4, 5, 6. And overall, it has 2 minus charge. So now I'll take a look at it. The Lewis dot structure. So if now you have 2 bars which are representing 4 valence electrons. Split that in half. You give 2 to the oxygen, and you give 2 to the carbon. Okay, and you split this one. You give 1 to this oxygen, and split that one. You give that one to this oxygen. Okay, so you give that one to this oxygen. So now you take a look at, for the central carbon, how many do you have? I have missed a 2 here because this is 2 split from here. Oh, I have to redo that. And split is 4, so 2 for oxygen, 2 for carbon. Split this one, 1 for the oxygen and 1 for the carbon. This one is 1 for the carbon, 1 for the oxygen. So in this case, I have 2, 1 for the carbon. I have the upstairs, the upper ones for the oxygen. I have 1, 2, 3, 4, 5, 6. I have this oxygen. I have 1, 2, 3, 4, 5, 6, 7. This oxygen, I have 1, 2, 3, 4, 5, 6, 7. So for this particular carbon, and also remember carbon, you should have 4 valence electrons. For oxygen, neutral 1, 1, 2, 3, 4, 5, 6. Those are for neutral atom. Okay, so in terms of the formal charge on this one, this is going to be 0. Okay, so this has 0 formal charge. Carbon should have 0 formal charge. Now for this oxygen, instead of 6, you have 7 valence electrons. So this one has a -1 charge, and that one has a -1 charge. So now you know formal charge on this oxygen is 0, on carbon is 0, on this oxygen is -1, on the oxygen is -1. Now you know where this -2 or 2 minus charge are coming from. It's coming from 2 oxygen atom. It kind of makes sense because the oxygen has a higher electronegativity than the carbon, so it should carry the negative charge. All right, so then let's go back to take a look at the sulfur dioxide situation. Look at the sulfur dioxide situation. So then you're looking at a sulfur dioxide. You have the resonance structures of sulfur, the oxygen, sulfur. You have 2, 2, 3, 4, 5, 6, and this has 2. Okay, and also the resonance structure of O, S, a pair, and O, and break down like that. Okay, so if you, for the process, for the formal charge, if you split this double bond, now you add 2 on the oxygen, add 2 on the sulfur. If I split this one on the 1, this one is add 1 here, so the sulfur 1 for the oxygen. So you're looking at 6 on the oxygen, so the formal charge will be 0, and you have 1, 2, 3, 4, 5. So now you should have 6 for the sulfur. So now this one's becoming +1, and this one actually has a 7, so this one is actually -1. So that's the formal charge, 0 + 1, -1. So now if you split this 2, I got 2 over here, 2 over here, 2 over here, 2 over here. Now you start notice each one of them have 6 valence electrons. So the formal charge is 0, 0, and 0. And here comes down for a very important note. Minimize the formal charge takes presidency let's see, erase this. Takes higher priority over octet, which means for the elements that can go over the expanded octet, the nature wants to assume the expanded octet in order to minimize the formal charge. As we can see on this particular one, and for the sulfur dioxide, the resonance structure, that cannot be for that. So you should have a pair here, a pair here. Because this has 0 plus 1 minus 1 is 0, 0, 0. This is preferred resonance structure. Okay, so this is a preferred resonance structure. Let's take a look at another example, and in this case will be sulfate ion. If you're running through all the steps, and just for the time's sake, I would like to speed up, so you'll have sulfur, oxygen, 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 2, 3, 4, 5, 6, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 3, 4, 5, 6. This is the one commonly written as the resonance structure, but you can, because of the sulfur can take more than 8, you can assume extended octet. You can do things. Oops, just excuse my handwriting a little bit. Or you can do it further. This, and this. And why not? Just keeps on going. Sulfur, because sulfur can take up to 18. Minus, and the last one, I'm quickly running out of space. Let's writing a little bit smaller. Those are all the possible Lewis structures for sulfate ions. But how could you tell which one will be the preferred one and the formal charge comes in? So if you start breaking them down, assign the formal charge, you will notice -1, -1, -1, -1, plus 2, because it only has 4 electrons compared to 6. So this one is going to be, put it back, so now 0, so this is -1, -1, -1, now it becomes plus 1. And this one will be 0, 0, 0, -1, -1. For this one will be, you'll have now 1, 2, 3, 4, 5, 6, 7, -1. So this one will be 0, 0, -1, and 0. For this one will be 0, 0, 0, 0, -2 on the sulfur. But you can now start realizing this is not quite reasonable, because sulfur has a lower electronegativity. Carrying a negative charge will be bad. This is even worse. The sulfur carrying -2 charge. So the best Lewis structure will be this, even though the sulfur is gone over the octet. But now you realize the -2 charge from the sulfate ion is coming from the 2 oxygen atoms. And this is the predominant, the best Lewis structure for sulfate ion. So with that, let's recap. The formal charge assigned for each atom in the molecule or polyatomic ion to help you 2 things. Determine which Lewis structure is the best, is the dominant one. That's minimize the formal charge and looking at the correct distribution of the charges on the polyatomic ions. That's actually the second one. Is looking at the which of the atoms in the polyatomic ion should properly carry the charge. Okay, so with that, I wrap up this podcast. Please refer to the worksheet for additional exercises. Thank you very much for your attention.